In my last video, I discussed the statement and proof of the Schwarz lemma. In this video, I'm going to discuss an application of the Schwarz lemma. So in some books, this is mentioned as Schwarz lemma, and in some books in complex analysis, this is mentioned as an exercise. Okay, so actually there are two statements in the Schwarz lemma. In this video, I'm going to prove the first statement, and I would do the proof of the next statement in my next video. Okay, so now if you remember what I did in the Schwarz lemma, in that case I had an analytic function from unit disk to unit disk, and that analytic function mapped origin to origin. So suppose I have an analytic function from unit disk to unit disk, and I do not know anything about what would happen to the origin under this function f. Okay, so now what I know is, I know that f is an analytic function from unit disk to unit disk, and that's what I know. Okay, I do not have the condition f0 equals 0. Okay, then what this pick lemma says is, if you pick any two different complex numbers from the unit disk, then this inequality holds. Okay, right. Let's try to prove this lemma, proof of the first part of the Schwarz-Pick lemma. Okay, right. So now we have to draw some diagrams when we are proving this lemma. I have the unit disk. This is my y-axis. This is my x-axis. This is the unit disk. My x-axis, my y-axis, and the unit disk. And I have my two complex numbers, z and w. Suppose w is somewhere there, and z is somewhere here. Okay, and this is the function f. Under this function, w would be mapped to fw, and z would be mapped to f of z. Okay, right. So to prove this pick lemma, I have to have some analytic function from unit disk, and that should map origin to origin. So what I'm going to use here is, I'm going to use disk automorphisms. Okay, if you have not heard about disk automorphisms, I would discuss about disk automorphisms in one of my future videos. For now, I would use them. Okay, right. So we have a self map from unit disk to unit disk like this. Okay, so right, so I have the unit disk here, and origin. So I need to map the origin to Z. Okay, so then this node would be important. Phi Z tau is equal to tau minus Z divided by 1 minus Z bar tau. 1 minus tau Z bar maps D to D conformally, and this map is onto. Okay, so that means I can define the inverse of this map. So what would be the inverse? Actually, you can calculate its inverse. If you calculate its inverse, you would get tau plus Z divided by 1 plus tau Z bar. Okay, so what I'm going to do, so what you can, if you consider the first map, you can note that tau Z, Z, phi Z, uh, should be phi Z, Z is going to be equal to 0. So that means this map phi Z maps Z to 0. So the inverse of phi Z maps 0 to Z. Okay, so what I'm going to do, I would use the inverse of phi Z that I define. Okay, this is phi inverse Z tau. Okay, right. So now what this map does is it maps 0 to Z. Okay, so under this map, 0 would be mapped to Z. So then I am applying function f to that. Then Z would be mapped to fz. So what I'm going to do next is x-axis, y-axis, and this is my unit disk. Right, so then I would apply a different map here. I would call that map as phi z. Phi tau. What I'm going to do, this is the psi fz tau. Okay, so it would be tau minus fz divided by 1 minus fz bar tau. Okay, right, so what does this map do? It would map fz to 0. Okay, this map maps fz to 0. Okay, so finally I have a map from 0 to 0. Okay, so I would denote this composition by capital Fz. This map, it is given by phi z inverse composite f. This should be tau, right? Yeah, be tau compose phi of fz. Okay, right. Now I have a composition of 3 analytic functions, and phi and psi are conformal and onto. Actually, they are bijections from unit disk to unit disk. So finally, I have an analytic function from unit disk to unit disk, and this capital F maps 0 to 0. Okay. So what is my F tau? It is I of fz compose with F compose phi z inverse tau. Okay. So yeah. Right. So, and I know this valid f0 is equal to 0. So by the Schwarz lemma, I have this result. If theta modulus is less than or equal to modulus of theta. Okay, right. So next I would go into, so this is valid for any theta in unit disk. This is for any theta in unit disk. Okay, so now next what I'm going to do is, instead of theta, I would plug some value in unit disk. So right, what I'm going to plug is, I have W here. So, and I would apply inverse of phi Z inverse. So that means uh, this is the inverse of phi Z. So what would be this direction? This is phi of Z. Okay, right. So right. So if you apply phi Z to W, phi Z W would be somewhere here. Okay. So since this inequality is valid for any theta, this is valid for any theta in the unit disk, I would replace theta by phi ZW. Okay. Replace theta by phi ZW means, because this inequality holds for any theta in the unit disk. Okay. Right. So I have f of theta modulus less than or equal theta. Now I would replace theta by phi ZW. Okay. So what is my capital F? That is phi of fz compose F compose phi Z inverse compose. Now instead of theta, I would plug phi Z of W less than or equal phi Z of W. Okay, right. Now phi Z is a bijection, so if you compose phi Z inverse and phi Z, you would get identity. So this would become an identity. So what would I get? Phi Fz compose F of W. Because if you apply identity to W, you would get W. Okay, less than or equal phi ZW. Okay, now on my left hand side, I have phi of Fz if W modulus less than or equal to phi Z W modulus. Okay, alright. So now I have my phi Fz. Yeah, this is my phi theta. So what I have to do, instead of theta, I have to plug FW for this function. FW, yes, FW. So what would I get then? On my left hand side, I would get, instead of theta, this is my theta, it's not 1, right? So sorry for my bad handwriting. So this is theta. So now instead of theta, I'm going to plug f of w. So what would I get? F of w minus f of z divided by 1 minus f z bar. I'm replacing theta by fw, right? And what do I get on my right hand side? What is phi z? Phi z is this map. This is my phi z tau. So I'm going to replace tau by w. So what would I get then? I would get w minus z divided by 1 minus w z bar. Okay. Okay, this is my final result that I need. Okay. Okay, actually I can interchange z and w. I can, because modulus of fw minus fz is same as modulus of fz minus fw. I can interchange those. So on my right hand side also I would interchange w and z. Okay, right. So this is what I need. Okay, this is the final result that I need. So in the next video I would discuss this fact. So you can try this if you'd like. So prove that equality holds if and only if F is a self-map. Okay, right. So this is what I needed to talk about Schwarz lemma. So in my next video, I would talk about the equality case and the next inequality that is connected to this big lemma. Okay. Okay. Thank you for watching. If you have any questions related to my proof, you can mention them in the comment section.